Dear professors, today I'm going to talk about the randomized algorithms. And in this lecture, we got to know that there are two types of the randomized algorithms. The first one is called the Las Vegas, and the representative one we talked about is called the randomized quicksort. And its characteristic is that it can always return the correct solution, but we have no idea with its running time. But and we also have the second type, which is Monte Carlo. Monte Carlo algorithm is actually it might return the wrong solution, but we have the trade-off that between the running time of the and the probability of the returning the correct solution. And the representative example is randomized min cut. And yeah, let's talk about the randomized quicksort firstly. The basic idea of the randomized quicksort is a quicksort, and the pseudocode is very simple. That the basic idea is that we keep comparing each element with the pivot every time, and here we got the first lemma 1, that the quicksort can always correctly sort the array. Even though we didn't specify which kind of the pivot strategy in the basic idea, but it can always sort the array. So how to prove it? We can prove it by the induction, and we firstly assume that when n equals to 0 or 1, it is very trivial that the quicksort can sort the array. And when n minus 1 time, we could easily find that we think it is hold. We assume it is hold, and it can always sort the quicksort. Sort the array. And when it comes to n case, we can notice that if we write the pseudocode here, the last line here would be the quicksort L plus x plus the pivot and plus the quicksort R. These two actually the size at most to be n minus 1, and we already said we assume the quicksort can always sort the array in n minus 1, so that's why why the n case is still quicksort can still sort the array. Yeah, and then we would like to we specify the strategy for picking the pivot in our basic idea. We just add one condition that we select the pivot uniformly at random, and we would like to know the running time of this randomized quicksort. And we already know that it's a randomized quicksort, so we might care more about the expectation of that. And from the procedure we have mentioned before, the running time depends on the number of the comparisons. So we show more interest about the expectation of the comparison times. So let xi to be we define xij equals to how do we get it? We just assume si to sj is actually a array that's sorted by the randomized quicksort. And we define xi we assume that s1 to sn is actually sorted by the randomized quicksort, and for any I greater than 1 and less than n, less than j and less than n, we define that xij is that si and sj could be compared between each other, and we observe that xij equals to be 0 or 1, and if if one of them is selected to be the pivot, then they will have the chance probability to get compared, and that's only one case. Otherwise, they will be never get compared. The value will be 0. So we can write the equation here. The expected sum of the I less than j and xij, and we already, by the linearity of the expectation, we can remove this sigma out of the in front of this, and then we can get this one. And this one we already see there is an indicator variable. So for event si and xj get compared, and because it's 0 or 1, so it's actually means si, the event si and xj get compared, the probability of that. So it can be converted into the sum of when I smaller than j and the probability of pij, that means the si and xj get compared. And we show we pay attention to this one. And here's the lemma 2, that it said that si and sj, we assume that sa to sb is actually returned by the randomized quicksort in the iteration, and si and sj will only get compared when they are the sort of the si of the array si to sj to be chosen as a pivot. How do we prove it? We assume that if c is less than I or greater than j, then that means these two elements will be put into the same side, and they will not get compared in this iteration, but they will together with each other to go into the next iteration. And we have the second case that if C is in the middle of the I and J, then they will never get compared because they are divided into two parts. And for the third case, if C equals to be I or J, then they will have the probability they got compared. So from this proof, we know that the Pij could be written like 2 divided by n minus j minus I plus 1. This is the probability of the Si and Sj get compared. And yeah, then we get this, and then we extend this sigma here to be this. And then we replace this part equals to k, and we saw that the minimum of the j is I plus 1, and so we replace with k. There is the minimum of k is actually 2, and the maximum of k is actually the n minus k, n minus I plus 1, and that's the conversion. Then we let's relax that. We just add more. Then we got this. Yeah. Then we have here we get proof that the running time of the randomized quicksort is actually in O of n log n time. Then let's move to the second example, the randomized mean cut example algorithm. The algorithm is still very simple. The mean cut problem is actually requires us to find a minimum set of the age. If we can remove the ages in the set, then our graph will be disconnected anymore. So and the randomized quicksort, randomized min cut is actually we choose the while the size of the vertices is greater than 2 and the edges is not empty, then we choose the edge randomly, and we contract them. We contract it and remove the self loops, and then finally we return the edge. Yeah, and yeah, we observe that we also define that if C is a min cut, then the lambda G is actually the size of the min cut. And we observe that during the iteration, the lambda G I is actually greater or equal to the size of the cut. And why this algorithm can always return the cut? We can still use the proof of the induction when we assume that we define that k which is smaller or equal to n minus 2. That means the iteration of the algorithm, and if k equals to 0 is trivial, and when k equals to n minus 1, we think it is holds, and when k equals to n, it actually says we get the we construct g prime from the g after the first contraction, and then we will return the cut by the hypothesis of the when k equals to n minus 1. So it can always return a cut in g prime, and also g prime the cut in g prime is also a cut in g. Yeah, and we prove that, and we need to explore some other probabilities. Like we observe that the specific, we show the interest about the probability that the specific min cut will return by the algorithm, and we observe that the specific C min cut is returned if and only if the previous iterations when we select the edges is not in C. So we let EI, E1, E2 to EI, En minus 2 to be the edges that we selected during the iteration, and G0 equals to G1 equals to G, and the GI minus 1 is actually equals to GI set minus EI, and we define the event epsilon E or to the epsilon n minus 2, and we define the epsilon E is the event that EI is not selected in C. So the probability we care more about is actually can be written like the PR epsilon. Oh no, it's actually a conditional probability, and we finally can get the our goal to be like I equals to 1 and n minus 2 pi, and where pi is actually a conditional probability. Pi is a PR of the epsilon E, and here this is epsilon 2 epsilon n I minus 1. Yeah, and then we show more about the explore this term, and pi is actually, we know that it's a probability that in the previous iteration, in the previous I minus 1 iteration, we didn't select the edges in C, and in this case, under this context, we in the ith iteration we still do not pick the edge in C. This is the probability of that, and we get 1 minus pi is actually means in the previous context and in the ith iteration we select ei in C, and we can know that it can be written like C, the size of the cut, divided by ei minus 1. And how do we know the ei minus 1? The relation about that, and we already know that how do we know that? We already see that the lambda gi must be greater than size of the C, and we know that lambda gi must be less or equal than the degree of the vertices in gi. That is because if we have if otherwise the min cut will not be min cut, because the cut in gi is also the cut in G. So that means the div is actually greater than the size of the lambda gi, and that's greater than the size of the C. And this is actually the 1/2 of the size of the E, and we get that. And then we already know that gi, the number of the size of the edges from gi is actually n minus I plus 1. That is because every time we reduce, we get after the contraction we reduce 1 point. Yeah, so we get to improve this, and this is actually finally get the n minus 3 and the n minus 3, and this is n, and times n minus 2 and we get the n minus 2 and 1. So we get the probability that the specific min cut is returned by the randomized quick sort min cut. And we also have the trade-off between this and the running time. If we would like to improve our probability of this specific min cut is returned, we can just run a lot of times of these algorithms to get the better answer, to get the best answer. So yeah, so we also have the final part, that the conversion of between the Las Vegas and the Monte Carlo algorithms. If we already have a Las Vegas algorithm and we would like to convert it from the Las Vegas to the Monte Carlo, what we need to do is just we stop it before it returns the correct answer, and then we get the then it turns to the Monte Carlo algorithm. And if we have the Monte Carlo algorithm and we want it to be the Las Vegas algorithm, what we do is just we repeat doing the Monte Carlo algorithms multiple times and until it finds a correct solution. So that's all.